The screen is visible?
Yes, sir.
Okay. So instead of practical, today we are going to conduct the class because we have to conduct in virtual lab. The bandwidth should be high for to conduct the virtual lab. For that reason, yesterday I will conduct the practical. Instead of that, today we'll cover the, and even the theory part has not covered for the next upcoming practical, that is two Wattmeter methods for unbalanced load and unbalanced load. So the yesterday class we have discussed the EMMC. It has three cases. Case one is emitter connection, case two is voltmeter connection, case three is that is wattmeter connection. Okay, just a minute. So roll number 9 and 18. So out of these three connections, in the yesterday class we have already discussed about the emitter connection, and the scale, whatever the scale of deflection is there, that is directly proportional to the I square. So square of current is proportional to the angle of deflection. We have already derived and shown the equation in this one here now. This is, so that is emitter connection. So the equation in the form of deflection in the form of current, we have derived the equation. For the voltmeter, we in the place of I, we have to derive the equation in the form of V. For the wattmeter, in the form of VI cos pi, we have to consider. VI cos pi, we have to consider that one. So for the emitter connection, we have, I told that one, the fixed coil and moving coil both are connected in parallel, and the load is connected in series with these two coils here now. But for the voltmeter connection, the moving coil and fixed coils are connected in series here now, are connected in series with the load also. It is connected in series only. We are going to consider here now. 28, 32. Okay, so see here, the fixed half of the fixed coil we have taken here now. Same the line here, joining continuation is there. Another half cycle we have, half of the fixed coil we have taken here now. Next, the moving coil we have placed in between the two half fixed coil, half fixed coil, and same connection it will continue to the high non-inductive resistance for the multipliers here now. To increase the range of this voltmeter, we are going to use here now, and that one it is going to connect to the load and to the negative supply here. So for the emitter connection, fixed coil and moving coils were connected in parallel, but for the voltmeter connection, fixed coil and moving coils both should be connected in series here. And for the emitter connection, we have added one shunt in parallel with the moving coil, which will increase to the, or to increase the, or to extend the range of emitter. Okay. So here, instead of shunt, we have connected a multiplier here now. Instead of shunt, we have connected a multiplier in series with this both the coils here now. One high resistance we have connected to extend the range of that voltmeter here. Fixed coil and moving coils are connected in series for voltmeter connection, and a multiplier may be connected in series to extend the range of voltmeter. To extend the range of voltmeter, we have connected a multiplier here now. Okay, the equation we are going to derive here now. See here, what is the torque equation? We have already derived. We have already derived the equation. TD equal to, what is that one? TD equal to, huh? TD equal to I1, I2, yes, dm by d theta. Yes, torque equation of EMMC instrument. If I1 and I2 are both are same, then we can use as I square. But in the rare condition only, we are considering that I1 should not be equal to I2. On that condition, I1 into I2 dm by d theta. We have already derived this equation here. The previous derivation only we have derived that equation. We have derived here. See here. I1 TD equal to I1 I2 dm by d theta here now. I1 is current flowing through the fixed coil, I2 is current flowing through the moving coil, and the mutual inductance between fixed coil and moving coil, that is rate of change of moving coil mutual inductance with respect to the angle of deflection we have considered here. Okay, with respect to the angle of deflection here. So based on this equation, the torque equation, how can we derive here? Now here for the ammeter connection, the I1 was equal to the I2. We are going to make that one both the voltage drop across the moving coil and the fixed coil we have made equal. Okay, for that reason the TD was I square dm by d theta it was. But for the voltmeter connection, first we have to derive the equation for the current here now. Derive the equation for the current, that is I1 equal to V1 by Z1 here now. See, according to Ohm's law, what is the formula for I? For the DC circuit, according to Ohm's law, what is the formula for I? I equal to, is it audible or not? Hello.
V upon R.
V upon R for the DC circuit. For the AC circuit, to consider it may be RLC load here now. RLC load is there. V upon what we can write? Yes, you all are diploma student, direct second year student. You should know this one at least. Have you heard the name of impedance? Have you heard the name of impedance? Hello all, I am speaking with you only. Hello. Z, I know that one. Have you heard the name? Impedance name, have you heard that one? Except roll number 6, I will you put absent today for all you peoples. You peoples will not give the answer, means why I have to waste the time here now. Simply I will explain and I will leave. I equal to, according to this one, I1 is the current flowing through the fixed coil and I2 is the current flowing through the moving coil. So we know that one, the voltage drop across the fixed coil is V1 and voltage drop across moving coil, that is called V2 we are considering here now. So the impedance of the fixed coil I am going to consider as Z1 and impedance of moving coil I will consider as Z2. So like in a DC circuit, like a resistance which opposes the flow of electrons, like in the AC circuit, which is a combination of resistance and reactance, that is called impedance, which is also opposes the flow of electrons or current in the AC circuits here now. So according to Ohm's law, V equal to V by R, I equal to, but in the AC circuit, V by Z we are going to consider. So voltage drop across this total impedance of the fixed coil, we are going to consider as Z1 here, and the moving coil impedance is Z2 we are going to consider. So I1 equal to V1 by Z1 I will use, and I2 equal to V2 by Z2 I am going to use here now. Why I am deriving the equation for I1 I2 means we already know that one, the TD equal to I1 I2 dm by d theta. The formula is there here now. Im I2 dm by d theta here now. In this place, which connection we are discussing here now? Voltmeter connection we are discussing. So we want the answer in the voltage here now. For that reason, that current I1 I am replacing that one into in the form of voltage here now. So I1 I will substitute here V1 by Z1. I1 I will substitute as V1 by Z1, and I2 I will substitute as V2 by Z2, and dm by d theta I will keep as it is here now. So by considering this one, the constant for the first one is, that is for the fixed coil, that is K1 we will consider. For the constant for the moving coil, that is called K2 we are going to consider. K1 V, and because V1 equal to V2 we can call that one, is nothing but V equal to V1 plus V2 we are going to call here now. So directly proportional. For that reason, what we are going to consider, V1 equal to K1V, we are considering V1 equal to K1V, the constant we are considering here now, K1V, and V2 equal to K2V here now. By substituting that here in the equation, that is 22. In the equation, this V into V, that is called V square. K1 and K2 I will consider as K here now, only one constant here now, and Z1 into Z2 I will write here into dm by d theta. The voltmeter connection we are discussing here means this is a constant only, Z1 Z2 K divided by Z1 Z2 is constant we are considering, and the dm by d theta also we are going to consider as constant here now. We can prove that the TD is directly proportional to V square here now, V square. Okay, so we know that TD is directly proportional to TC, or TC is directly proportional to TD. TD is directly proportional to V square. So can I write here now, TC equal to K theta is there. So TC is directly proportional to theta also here now. Theta is nothing but proportional to. Can I write this one directly? Theta is directly proportional to V square.
Yes,
Or we can do that. We can do that directly instead of writing directly here now. So we can derive this equation, TD equal to V square by Z1 Z2 and dm by d theta. So we already know that TC equal to TD here now. TC equal to TD, we know the formula here, TD. Okay, now you substitute TC equal to K theta, we know that one, K theta, and TD equal to, you substitute this formula here now, and KK gets cancelled over there. KK gets cancelled. V square Z1 Z2 and dm by d theta we can consider as constant here now, d theta. So this complete term we can consider as constant here now. So we can write here theta is directly proportional to the V square. We are discussing here for the voltmeter connection here now. So the deflection, the angle of deflection is again here square of the voltage here now. For that reason we can say that the scale is not uniform again here. The scale is not uniform, we can say again here. because theta is proportional to, not proportional to V. Theta is proportional to V square is there. So again, we can say that the scale is not uniform. The angle of deflection is directly proportional to the square of the voltage, supply voltage. You can tell that one. This is the case 2 explanation here. Case 2 explanation. Next, we'll go for the case 3, that is called wattmeter connection. This is a little bit different as compared to the voltmeter and emitter connection. Little bit different is there. What is the different means? Here, the load is connected in series with a fixed coil. The load is connected in series with fixed coil, but the load is connected in parallel with the moving coil. In parallel with moving coil. So the combination of this is actually we are going to use for the measurement of power here. Now we can use this one as wattmeter connection here. Now see here, the fixed coil is connected in series with the load and moving coil is connected in parallel with the load here now, and the current flowing through the fixed coil, that is called I1, current flowing through the moving coil, that is called I2. To this one, to neglect the impedance of the moving coil, we have considered one resistance here now, which is connected in series with the moving coil here now. The moving coil we are going to consider as voltage coil here now. We can measure voltage drop across this one. The fixed coil we can consider as current coil. We can measure the current here now. The product of voltage and current, what is it? It is nothing but product of voltage and current. It is nothing but, I will not ask at all. It is nothing but power here. No, according to the DC circuit, P equal to VI, but in the AC circuit we are going to consider P equal to VI cos phi. VI cos phi. Cos phi is nothing but angle between the voltage and current. We can call that one here. No, it is nothing but power factor. Cos phi is a power factor. Phi is nothing but angle between voltage and current. We can say that one here. So the fixed coil we are going to consider as current coil, and moving coil we are considering as voltage coil here. Now the voltage coil is connected in parallel with load and fixed coil is connected in series with the load here now. So same thing I have written here now. When the two coils are connected parallel here now, both the coils are connected parallel only, the instrument can be used as a wattmeter. These two are connected in parallel only. This current flowing through the I1 is different, current flowing through the I2 is different. Both are in parallel, but fixed coil is connected in series with the load. This one, it is connected in series with the load, and moving coil is connected in parallel with the load here now. So the moving coil is known as voltage coil. This coil is known as voltage coil, or pressure coil we are going to call, and fixed coil is known as current coil we are going to call here. So we already know that the current, whatever the power is the product of voltage and current here now. So the emitter is connecting in series here now. Then from the current coil we can measure the current. From the voltage coil or pressure coil we can measure the voltage across this one. So the product of these two and angle between these two, it is going to give the power here now. So V equal to Vm sin omega t we have considered here now. According to this, we can write here I2 equal to, which across this one, this point only we have considered voltage here now. So voltage current flowing through this one, I2 equal to Vm by, actually the impedance of this coil is neglected here now. Vm by, what is the R? We can use this one, R sin omega t we can write. Sin omega t current formula. If the angle between the I1 and I2 is, we are going to consider as phi here. Suppose the phase difference is phi is there from I1 and I2. On that situation, we can consider this Vm by R equal to, we can consider as Im also, or I1 equal to Im directly the maximum current sin omega t minus phi. We can consider like that also. Sin omega t minus phi. Sin omega t minus phi. We can write like this here. So this is the I1 equation, I2 equation we got here now. So substituting in the torque equation, we are going to get here now. Here Im we will get, Vm we will get. The maximum value divided by √2, √2 will get by average value by doing the average value of that one. So obviously we will get the power equation here. Assume that the supply voltage is AC here now. Sinusoidal is there. If the impedance of the coil is neglected in comparison with the resistance R here now. Comparing with that this resistance, it is impedance of this coil we have neglected here now. For that reason, V equal to Vm sin theta sin omega t they have considered, means I2 equal to Vm by R we are considering here now. Im R Vm by R sin omega t, both are same only we have considered here now. So I will write in the equation, I will show here the same equations here now. We can tell that one I2 equal to Vm sin omega t divided by R we have considered. Let the phase difference between the currents I1 and I2 is phi here. I1 and I2, in between these two here, suppose the I1 is there. This is I1 and this is I2 here now. This is I2. The phase difference between these two is phi is there. These two is phi. So I2 we have already written here sin omega t here now. Vm by R into sin omega t. So I1 is lagging the I2 by an angle of phi. So I1 equal to Im sin omega t minus phi we have written here now. For the lagging, we are going to use minus phi here. So according to the torque equation of the EMMC equation, we already know that TD equal to I1 I2 dm by d theta. I1 I2 dm by d theta. Substituting this I1 value, I2 value in this equation. Already I1 equal to Im sin omega t, I2 equal to Vm by R sin omega t here now. I1 I will substitute Im sin omega t minus phi. I2 Vm sin omega t divided by R here now, dm by d theta. 1 by R or Vm Im by R, I can take outside here now. Im Vm sin omega t minus phi here now. So see here, Vm, the RMS value is Vm by √2 equal to V, Im by √2 equal to I, we can get that one here now. But by doing this average value of this one here now, the average of this one, we are going to get the equation in the form of cos phi. That is the average equation. I will show here where it went. Okay, the average deflecting torque we can write as TD is directly proportional to K. 1 by R, the resistance is constant, we can consider as K here now. So this sin omega t minus phi, it will give the cos phi, and this one we are going to consider as constant here now. So Im by 2, actually this sin omega t minus phi, it is nothing but cos phi divided by 2, na? Again I am asking questions, sorry for the asking the questions. So it is nothing but cos phi divided by 2. So divided by 2 is there, actually that is Im by, I will split into √2 into √2. The 2 term I will shift into √2 into √2. Im by √2 is I, Vm by √2 is V. This term we are going to consider as cos phi. So other things we are considering as constant here now. So Vi cos phi is there. The answer we are going to get, the average value of answer, we are going to get Vi cos phi. So Vi cos pi is the equation for the power here now. So for that reason, TD average we have called here now, KVI cos pi. We know that when TD equal to TC and TC is directly proportional to the theta, then in the place of theta, theta is directly proportional to TD, we can write here now. TD equal to KVI cos pi, K is the constant, we can write theta is directly proportional to the Vi cos pi. Vi cos pi is nothing but our power only. For the wattmeter measurement, the angle of deflection is uniform. The scale is uniform, we can call that one here. Here, the 1 point it shifted means 1 watt it is going to shift like this here. The scale is uniform for the wattmeter measurement of the EMMC here. So the electromagnetic moving coil we can use as voltmeter, current and voltmeter, ammeter, and wattmeter here now. It completes the EMMC here now. It completes the EMMC. Any doubts? Before starting the next topic, if you have any doubts, you can ask.
Sir.
I'm asking to you people only. If you have any doubt, you can ask.
No, sir. No, sir.
Okay. The next topic is measurement of three-phase power in three-phase circuit. Actually, measurement of three-phase power. You can tell that one here now. So we just now we have discussed about the wattmeter method here. Now by using the wattmeter, we can derive, we can measure the power. Okay. For the three phase, each phase power we have to derive. Each phase 1 power, phase 2 power, and phase 3 power we have to calculate. We have to measure that one. Then summation of P1, P2, P3 equal to total three phase power. We will get that one, according to the principle of the three-phase circuit here. Now P1, P2, P3 here. Now see here, just now we have discussed the EMMC. It has here current coil is there. This is pressure coil here. One is connected in parallel series, both are connected in parallel here. Now this is one wattmeter. For the second phase, again one current coil, one moving coil or pressure coil we have connected, that is wattmeter 2. And for the third phase also wattmeter 3. All the three phases, each phase is connected by one wattmeter here. The phase 1 is connected by wattmeter 1, which is we are going to mark as P1. The phase 2 is connected as one more wattmeter, that is called P2 you have connected. The phase 3 is connected to another wattmeter, that is called P3 here now. The star connected load we are using here now. The neutral point we are connecting here now. The pressure coil of that one we are connecting to that neutral line here. We are connecting as neutral line here now. The pressure coil, whatever the pressure coil other terminal is there, we can connect here, or directly here also we can connect here. So it is star connected load here now. The current flowing through the phase 1 is I1. Current flowing through the phase 2, that is called I2. Current flowing through the phase 3, that is called I3 here now. So actually P1 equal to V1 I1. P1 equal to V1 and I1 here now. Both are the in the polarity will be same here now. V1 I1 and P2 equal to V2 I2. P3 equal to V3 I3. So we know that one P1 equal to V1 I1. We can write P1 equal to V1 I1. Instead of that, I will take the text here now. So P1 equal to V1 I1, V1 I1. P2 equal to V2 I2. P3 equal to V3 I3 here now. V3 I3 here now. Three phases are there, three loads are there here now. The current flowing through that load and voltage drop across that load. Current flowing through the second load and voltage drop across the second load. Current flowing through the third load, that is, and voltage drop across that one here. It will give three powers are there, three powers, that is P1, P2, P3 we have considered here now. The total power of the circuit, we can tell that one total power P equal to P1 plus P2 plus P3. This will give the total power here. Total power we are going to get here now. So this at this point C we are considering as the reference for the that coincidence point. Also you can consider voltage drop across that point C will be 0 is there. Voltage drop across that one will be 0 here now. For that reason, so voltage drop across the first phase, that is called V1, V2, V3, V equal to V1 dash, V1, V2 equal to V2 dash, like that. The voltage we have considered here now. Okay. So the total power P equal to P1 plus P2 plus P3. We can do calculation also, or by whatever the measured value is there from wattmeter 1, wattmeter 2, wattmeter 3, summation of these three values, by doing that one also we are going to get the same equation only. We are going to get the same equations. Actually, there are two methods are there for the measurement of the power, by using this 3 wattmeter method, as well as by using 2 wattmeter method also it is possible. Instead of using this 3 wattmeter for each phase 1 wattmeter, we can, by using only 2 wattmeter also, we can measure the power. First we'll discuss the 3 wattmeter power. The connections as employed for 3-phase 4-wire system here now, 1, 2, 3, and this is the fourth one we have considering here now, as shown in the figure. In this case, the common point C here now, the common point C we have taken of pressure coils, and the neutral O of the load coincidence here now. See here, connected in star, all the 3-phase loads are coincidence into one point, that is called O, or neutral we are going to call that one. And the whatever the pressure coil other terminal it is connecting coincidencing here now, both are short circuited here now, and voltage drop across that is 0, we are going to call that one here. So the sum of instantaneous reading of the wattmeters here now, sum of instantaneous reading we are telling here now, P equal to P1 plus P2 plus P3 here. Can call that one here now. We know that P1 equal to V1I1, P2 equal to V2I2, and P3 equal to V3I3. By substituting that, the instantaneous power of the load is V1I1 plus V2I2 plus V3I3. Hence, these three wattmeters measure the power of the load. For each phase, one power we have connected, and by measured value P1, P2, P3 values, I will sum that one by adding all the values together. The total power of the circuit we can measure here. Now, this is called 3 wattmeter method. If you have any doubts, you can ask now. This is 3 wattmeter method. Even you can connect this one as in the delta load also. Star and delta both will get the further between one phase to another phase. You can connect one wattmeter here. Now for each phase you can connect one wattmeter, then you will summation of all that one, it is going to give that one same answer only. You can use 3 wattmeter for the delta load or star load. Both the answers you are going to, means we can calculate for star and delta load, both it is applicable here now. Any doubts?
No, sir.
देखो इंटरेक्शन नहीं है तो अभी 20 क्लास में मैं पूरा सिलेबस कंप्लीट कर देता हूँ. If you are not ready to interact, then I will directly I will start explanation. Then it will, within 20 hours it is the whole syllabus will complete. Already for 15-16 classes are over, still we are in second in it. Simply explanation is like watching a movie. Whenever will come for the interaction, then only something will enter into your mind. You remember that. So next method, that is called measurement of power in 3-phase circuit by using only 2 wattmeter method only. Instead of these 3 wattmeters, I am going to use only 2 wattmeters only. This common point is there. Instead of this common point, I am going to use one phase as common here now. One phase as common here now. I will remove the third wattmeter. This pressure coil of this one I will connect here, and the another pressure coil common point I will use as here now. So the power consumed by 1 to 2, phase 1 to 3 and phase 2 to 3, by doing this one, addition of this P1 and P2 also will get the same output here now. Will get same output, will get that one. That one we are going to prove that one here. In the next equation, we have to prove that one. So 2 wattmeter methods here now. 2 wattmeter methods. In 3-phase 3-wire system, we require 3 elements. Okay. But if we make a common points of the pressure coil coincidence with one of the lines, in these 3 phases, I will consider one phase as a common pressure coil coincidence point over there. Then we'll require only n minus 1 elements here. Now, if 3 phase is there, 3 minus 1, 2, 4 phase, 4 minus 1, 3, like that. 1 minus 1 term here we are going to use here now. 2 elements only is required here now. So the instantaneous power consumed by the load is V1 I1 plus V2 I2 plus V3 I3. This formula we have to prove from all the equations here now. We have to prove from these equations, or next circuit we have to prove the instantaneous power consumed by the load is V1 I1 plus V2 I2 plus V3 I3. We have to prove here. Let us consider 2 wattmeter connected to measure power in 3-phase circuit as shown in the figure here now. Star connection and delta connection, both the circuits. अब तब बोली, unmute please. तांबोले अब तब, even I have not marked your attendance as present. अब तब तांबोली, you have not entered your roll number in the order, and even without only the name displayed for me, for that reason I am not going to give you present. Okay, see here, this is the circuit diagram. 3-phase circuit, star connection we are using here now. So comparing with 3-phase 3 wattmeter methods here now, only 2 wattmeter methods we are using here now. The phase 1 is connected with 1 wattmeter, phase 2 is connected 1 wattmeter, but phase 3 is there is no wattmeter at all here. The pressure coil, another terminal, the common point we are considering as phase 3 only here now. It is connected to here, and the coil 2 also, the pressure coil is connecting to here. So the third phase we are considering as common point here now. Common phase we are considering for here now. Suppose we are going to measure the voltage between 1 and 3 and 2 and 3 here. The current flowing from 1 to 3 and 2 to 3, like that we have to measure here. Like that we have to measure here now. So what we have to do now, from the star connection, this was star connection, the current flowing from 1 to 3, that is called I1, we are going to consider here. No, I1 is flowing here, but this is, we are giving the supply here. No, the common point is 3 only we are using. So the current will, whatever the voltage we are going to measure here, that is this one I1 into here now. So I1 will flow here now. So voltage drop across phase 1 and voltage drop across phase 3, it will give the voltage, total voltage, and current is I1 here now. So the instantaneous voltage by wattmeter P1 is nothing but I1 into the voltage V is here. The direction is opposing here now. The polarities of this one is positive, negative, and this one positive, negative is there here now. So V1 minus V3 we are going to consider here now. V1 minus V3 here now. So P1 equal to, I will use the text again. P1 equal to I1 into V1 minus V3 here now. That is called P1 here now. Next, similarly, from 2 to 3, which current is flowing here now? I2 is flowing here now. The voltage drop across the phase 2 is V2. Voltage drop across the phase 3 is V3 here now. Again, we have to make this one as V2 minus V3 into I2 here. So P2 equal to, I will make enter here now. P2 equal to I2 into V2 minus V3. That is called P1 into P2. So P1. So the total power P equal to P1 plus P2. P1 plus P2 here. Substitute here now. P equal to, I will write P1 is I1 V1. I will write directly. So you multiply this one I1 into V1 here now. I1 V1 minus I1 into V3. I1 into V3 plus this one P2 here now. P2 equal to I2 V2 minus I2 V3 here now. I2 V2 minus I2 V3. We can do like this here. Next here now. I1 V1 you keep as it is here now. I2 V2 you can keep as it is. P equal to I1 V1 plus I2 V2 plus or see here. This term you consider here minus I1 V3, here minus I2 V3 is there. Both side minus is there, minus V3 and minus V3. You can take this one as common here now. Minus V3 I will take common here. What is the left term here now? I1 plus I2. I1 plus I2. We can write like this here. I1 plus I2 here. So at the point, this point here, I will erase this part. I erase this part. See here, at this point, the current coming towards this O, this I2 is also coming towards O, I3 is also coming towards O here. According to Kirchhoff current law, the currents meeting at a junction is equal to 0. So incoming currents are considered as positive, outgoing currents are considered as negative here now. So according to that, I can write I1 plus I2 plus I3 equal to 0. I1 plus I2 plus I3 equal to 0. From this equation, you consider, you write the equation for I3 here now. If I will consider I3 equal to, when I will send this I1 and I2 into RHS side, it will become minus I1 minus I2 minus I2. This equation we can write as I3 equal to minus, you take common here now, I1 plus I2. I1 plus I2. Here minus I1 plus I2 is there. Here see here minus I1 plus I2 is there. This in this place of minus, I can make this one as plus, and can I substitute in the place of I1 plus I2, that is I3 here now. This minus into minus, it will become plus. I1 plus I2 equal to I3 here now. Can I substitute? At least now also you can give the reply.
Yes, sir.
V1 P equal to V1 I1 plus V2 I2 plus V3 I3. So hence it is, the power equation is proved here now. What is the instantaneous power? P equal to V1 I1 plus V2 I2 plus V3 I3 only we have to prove. Na? That one only we have proved here now. How many wattmeters are there? Only 2 wattmeters are there. From these 2 wattmeter, see, by you substituting this equation also, from P1 and P2 only 2 equations only, we have derived this equation here now. V1 I1 plus V2 I2 plus V3 I3. So same thing, we can say that here now, instantaneous reading of power P1 wattmeter, instantaneous power P1 equal to I1 V1 minus V3 and P2 equal to I2 V2 of minus 3. So substituting P equal to P1 plus P2, P1 value substitute here, P2 we have substituted here, splitting this one I1 into V1, so that is V1 I1 minus I1 into V3, we have V3 I1 plus I2 V2 minus I2 V3 here. Now from this one term we have taken minus V3 outside, I1 plus I2. According to Kirchhoff current law, the summation of current, algebraic sum of current meeting at a point or junction is equal to 0 is there. So I1 plus I2 plus I3 equal to 0, or I3 equal to minus I1 plus I2. We can substituting here, we'll get the instantaneous power, that is called V1 I1 plus V2 I2 plus V3 I3. Therefore, the sum of the two wattmeter reading is equal to the power consumed by the load. This is irrespective of whether the load is balanced or not. It is irrespective, the load is balanced or not. We are going to get the power P equal to VI, V1 I1, V2 I2, V3 I3. If it is not balanced, then we will get different answers. That's it. The phase one power 1 is different, power 2 is different, power 3 is different. If it is balanced, this power is equal to this equal to this here. All powers are equal. So another one, we'll finish that one, this part complete. Another one is by using delta connection here. Can use the delta connection. By using the delta connection also you can consider here. See here the I1 is current is flowing here. Now I3 is coming towards here now. So this point, the junction node current we can consider as I1 minus I3 we are writing here now. Here I2 minus I1 we are writing here now. I2 minus I1 we are writing here. So here also same, the delta connection, that only two wattmeters only we are using here also. P1 and P2 only we are using here. No. So the instantaneous power between 1 to 3 here. No. 1 to 3. Which load is there? It is V3 is there. Yes. Which load is there here?
Yes, sir.
V3 is there. So for the V3, the polarity is reversed here. No. 3 to 1 is there, but we are measuring from 1 to 3 here. No. So we can write, I'll try to again use the text here now. P1 equal to, can write P1 equal to minus V3, which current it is related? I1 and I3 here now. So I1 to I3 here now, again it is reversing here now. So we can write I1 minus I3. We can write I1 minus I3, P1. Next for the P2 equal to, so 2 to 3 we have to calculate here now. From 2 to 3 here now. Which load it is connected here now? V2, second phase load here now. So voltage drop across it is in the same polarity, 2 to 3 only. The voltage polarity is there. So directly I will write V2 here now. The current is related to here means I2 and minus I1 is coming towards at this junction here now. So I2 minus I1 we can write here now. I2 minus I1. Yes. So next you substitute total P equal to P1 plus P2. Again same equation we are going to write here now. Next P equal to P1 equal to this one minus V3 into I1. Minus into minus, that is plus here now. I will write here direct minus V3 into minus V3 into I1 minus into minus, it is plus. So plus V3 I3. Next P2 equal to V2 I2 plus V2 I2 minus V2 I1 here now. Minus V2 I1. Next P equal to, I will write P equal to, see here the V1 term, where it is there is no V1 term at all. Where is the I1 term? Here the I1 term is there. Here the I1 term is there. Here the I1 term is there. Both sides the minus sign is we are using here now. So minus I1 I will consider as outside. I will take that one minus I1. So the term left is V2 plus V3 here now. V2 plus V3 is left here now. I will write it as it is. Next V2 I2 plus V2 I2 plus V3 I3 is the left here. Up to here it is we are using here now. Next consider this balance delta connection here now. See, it is a closed conducting path here now. It is a closed conducting path. According to Kirchhoff voltage law, the voltage drop across load 1, load 2, load 3 here now. The algebraic sum of the voltage drop across each resistance is equal to 0 here. So V1 the polarity is same here now. V2 the polarity is same here now. V3 the polarity is same here now. So V1 plus V2 plus V3 we can write equal to 0. V1
Yes, sir.
plus V2 plus V3 equal to 0, equal to 0. From this equation, V1 equal to, what is the formula? V1 equal to, V1 I will keep here only, V2 and V3 I will send into RHS side, it will become minus, yes, minus V2 plus V3 here now. Like this we can write. See here minus V2, sorry, minus is there outside, V2 plus V3 is there. In this place, we can substitute V1. Minus V2 plus V3. Here minus V2 plus V3 is there. In this place, if I have substituted, P equal to, in the place of minus, I will minus into minus, this minus into this minus, it will become plus. I will substitute I1 and V2 plus V3 is V1 here now. So we can write V1 I1 plus, same as it is, V2 I2 I will write as it is, V2 I2 plus V3 I3. Hence the instantaneous power is proved here now. Hence the instantaneous power is proved here now. This one only we have to prove, na? P equal to V1 I1 plus V2 I2 plus V3 I3. We have proved here. So same thing we have written in this explanation here. Now the instantaneous reading of P1 wattmeter here. Now P1 is the power across in between 1 and 3 phase here. That is the voltage drop here. Now polarity is reverse, that is minus V3. So I1 minus I3 we are considering here now. At this point, I1 minus I3, only this point we are considering here now. And similarly, the instantaneous power reading of the P2 here now. P2 is 2 to 3 it is flowing here now. It is in the same polarity, so V2 we have considered. So I2, that current meeting at this point is I2 minus I1 here now. I2 is going away, I1 is coming towards here now. So I2 minus I1 we have to consider. They have written wrong this one here now. I2 plus I1 they have written, it is not correct. It is I2 minus I1. The equation how they have used. Okay, here see, I2 minus I1 only they have used. This is minus symbol we have to use here now. Then the summation of P1 plus P2, we by doing this one here now, the P1 equal to minus V3 into I1 minus I3 plus V2 I2 minus I1. By splitting this term here now, V2 I2 plus V3 I3 minus I1 V2 plus V3 will get that one. According to Kirchhoff voltage law, we know that one by it is a loop here now. By loop analysis, by applying that one, V1 plus V2 plus V3 equal to 0 here now. So V1 equal to minus V2 plus V3 here. By substituting here minus V1 here, V2 plus V3 equal to minus V1, we substitute here. Minus into minus, it will become plus. So V1 I1 here. So the summation of this total power will get the instantaneous power is V1 I1 plus V2 I2 plus V3 I3. So it is the power we can measure. The three-phase power we can measure by using only 2 wattmeters only. It is also possible here. Now we have proved the equation here. If you have any doubts, you can ask. Any doubts?
Okay.
Just a minute, I will take the attendance. I will mark the attendance. 3, 4, 5, 6. 7, 8, 9, 10. Rule number 11. Rule number 1, rule number 2, rule number 11. Rule number 17. Rule number 19. 21. 26, 27, 29, 31, 36, 37, 39. Okay. The tomorrow class, Same this 2 wattmeter method once again I will explain, and we'll do the practical on this one here. Now for balanced and unbalanced condition, we are going to conduct the practical on this theory part only. It is going to help for the tomorrow lecture. For that reason only I have conducted a theory lecture for today. Okay, stop here only and we'll continue in the next class.